So we left off momentum and impulse. I said I was going to write these up and then talk about them. So let's jump into it. Momentum and impulse. So I guess the big thing to remember here are really two things. Impulse, there's a couple ways to think of impulse: area under force versus time. It gives motion to an object by a force. Impulse is the force being applied to the object, getting it up to some speed, changing its momentum. All right, momentum is motion. It's mass times velocity. And if you know an object's momentum, you know a lot about it. You can figure out how it's going to hit something, what kind of force it's going to apply, how far it's going to go, all kinds of stuff you can know about an object with its momentum. You can figure out its mass, you can figure out its velocity, you can figure out its kinetic energy, in fact. So forces cause changes in motion. So forces applied for a certain amount of time cause a change in momentum. Collisions, when two or more objects collide, the total momentum of the system is conserved. That's an important fact. Basically, when two objects hit each other, they apply a force on each other. Well, they must apply an equal and opposite force to one another, Newton's third law. So if they apply an equal and opposite force to each other, and they obviously also must have been in contact for the same amount of time, they give each other the same impulse, except one of them's negative, one of them's positive. So the ball, like if these two spheres hit, right? The one on the left here, it's getting hit to the left. It has a negative impulse. The one on the right here is getting hit to the right. It has a positive impulse. The total impulse given to this system of collision is zero because there's no outside force. They're hitting each other. So the net change in momentum, the net impulse, all has to be zero. So that's why momentum is conserved. Whatever total momentum you start off before the collision with is how much you must end with at the end here. So let's just look at these notes really quick. Force and time. If something hits, the force builds up, then it goes down. Anytime two things hit, it's not just like an instant amount of force. It's they hit, they collide, they bounce off each other and go away. So the force increases, it peaks, then it goes down. The area under this curve, if you did 1/2 base times height, the units would be Newton seconds. That is the definition of impulse. So that area under the curve could be used to determine the object's change in momentum. So the symbol for impulse is this J. Symbol for change in momentum is delta P. So impulse causes change in momentum. Force times time is impulse, if we're just talking a constant force. Mass times change in velocity is the change in momentum. So either one of these, right, J equals force times time equals m delta V, you could think of this as like a cross equality as well. Change in momentum can be force times time, since change in momentum is equal to impulse. Impulse can be mass times change of velocity, since impulse equals change of momentum, right? So, it's pretty simple stuff, but it can get a little confusing. The practice problems we did in class, but I'll quickly go over them. We've got a positive 5 Newton force acting on a 2 kilogram block on a frictionless surface for 3 seconds. So there's the drawing there. There's the block, the force, the time. So we know the force, the time, the mass, right? We know the force, the time, the mass. We don't know the change in velocity. That's essentially what we're going to be looking for down here in part B. So determine the impulse given to the object. J equals force times time equals m equals force times time. Positive 5 newtons, 3 seconds. Positive 15, ooh, wrong units on there. Newton seconds. Positive 15 Newton seconds. All right, that's the impulse. So that's going to be wrong in the printed solution. on the copied solutions. Hopefully somebody will notice that and be like, Mr. Harmon, why is that meters per second? Because I was going way too fast when I made this. All right. So if the object starts from rest, determine its final velocity, including magnitude and direction. So, all right, so now we got to use this, J equals positive 15 Newton seconds, and set that equal to the mass times the change in velocity, right? When we deal with rocket science, rocket motors give an impulse to an object, which causes a change in velocity of the object. Well, if the mass is big, the change in velocity is small. If the mass is small, the change in velocity is big, because you can't change the impulse given by the engine. That's set at the factory. That's based on how much gunpowder's in there. You can change the mass of your rocket, though. Keep it light, you're going to get a bigger change in velocity, right? This product of mass times velocity is equal to whatever the engine is giving it. So J equals delta P equals positive. Why did I do meters per second on all these Newton seconds? That's just so weird. All right. Delta P equals 15 Newton seconds. 15 Newton seconds. Got to set that equal to M delta V. Delta V equals 15 Newton seconds over 2 meters. Do the math, you get positive 7.5 meters per second. Now, we spent some time in class on this, but if the change in velocity is 7.5 and it starts at rest, that must mean your final velocity is 7.5 meters per second. All right, collisions, there it is. We went through this one pretty carefully in class. I'm not going to spend too much time on it. You know, I'm not going to reread the whole thing here. We've got a 1.5 kilogram block traveling at positive 4 meters per second. We've got a 6 kilogram block initially at rest. This incoming one hits this one. Because this one's bigger, the smaller one bounces off. Bounces backwards at negative 0.25 meters per second. This one must go off to the right. Because when they collide, right, the one on the left, incoming one, gets hit head on, well, it runs into the stationary one. The force of contact is pushing the smaller one to the left. It's pushing the bigger one to the right. The bigger one absolutely must move to the right. There's no choice there. This one might not bounce backwards sometimes, right? Because it could end up, that force that it gets applied to it when it hits this block could end up just slowing it down and stopping it. It could slow it down and it could keep moving forward slower than this one and so on. But anyways, the way to actually do this is to say P before equals P after. Remember, this is the mass times velocity of each object, right? Mass times velocity of the first one. Mass times velocity of the second one. This one's just 0 because it's got no velocity. Mass times velocity after of this one, negative 0.25. Don't forget the negative side. 6 kilograms times V for this one. But that's just a matter of doing the math, right? I dropped the units on these. It was 6 equals negative 3.8 plus 6V. So you got to add 3.8 to both sides. 6.38 over 6 is about 1.1. And the answer comes out positive, so the big one moves to the right. Same setup here. 2 cars, they collide, they stick together, they slide off the road. So they're both moving initially this time. So 1,300 kilograms, positive 15 meters per second. That's MV for this one. 1,100 kilograms plus times positive 8. That's MV for this one. Solve each one of those, add them together. You get 28,300 kilogram meter per second equals 2,400 V. Divide both sides by 2,400. V equals 12 meters per second. All right. 12 meters per second. Very cool. Good problem. When they stick together, you treat them as one object stuck together. Remember that. That's important. You could treat them separately, but then you end up with 1,300 times V plus 1,100 times V. At some point, you're going to have to combine them together and factor out that V. So I just like to do it right in the beginning of the problem. All right, circular motion, gravitation. We'll do this, and then I'll stop this video and upload it, and then I'll do the final static electricity and circuits one to finish out things. So centripetal acceleration, you kind of have to start with centripetal force. The centripetal force is the force that pushes or pulls something in a circular path. Remember, centripetal can mean central acting. That's what centripetal means. Central acting force, which makes sense. That's a fun way to say it. So that force that pulls something in a circle, it could be any number of things, right? It could be tension, friction, normal force, could be gravitational force if you're talking about an orbit of a satellite or planet or something. So centripetal acceleration is the acceleration that goes with centripetal force. That's kind of hard to imagine, centripetal acceleration, because it's the acceleration directed towards the center of an object's circular path. All right, still in meters per second squared, centripetal force is in newtons. It's just a little weird. Now, gravitational force, every object that has mass attracts every other object that has mass, right? And they apply an equal and opposite force to each other. They pull on each other. Now, if they're just let to go, they would crash into each other, create one new mass, conservation of momentum. If I started at rest, let them go, they'd hit, and whatever the initial momentum was would be the final momentum. Now, let's see here. The key here, though, is where does this come from? Well, that's a mystery of science. Though we know how to calculate it, we know the equation to predict it, but what gravity actually comes from is a bit of a mystery. It's definitely proportional to the product of the two masses, inversely proportional to the distance between them squared, and proportional to this constant, big G, gravitational constant, which is this big, small number. Big in terms of number of digits and such, in units, but small number. So, basically what you need to know here is the bigger the mass is, the more the gravitational attraction between them. The closer they are together, the more the gravitational attraction between them, because R's on the bottom. You make that smaller, this equation result goes up. But, we'll see that in a second. So practice problems, 200 kilogram go-kart goes around a 4-meter radius arc turn at a speed of 15 meters per second. All right, so the cart's going around the turn, centripetal force acts towards the center of the circle to keep it on the road. I'm immediately going to answer the last part here. It's friction. When you go around the corner in a car, it's the force of friction acting on the tires that keeps your car on the road. If there's rain, if there's snow, ice, that all impedes your friction. So it's harder to go around a corner. And what do? You slow down. You have to slow down to be able to navigate the turn. So that's because centripetal force equals mv squared over r, right? So the force, the way I like to think of this is it's the force required for an object to move in a circular path at a certain speed, right? So this is the object's mass that's moving in the circle. This is the speed it's traveling at, and this is the radius of the circle. So the bigger the radius of the circle, the smaller the force needed. The bigger the velocity, the bigger the force needed, which we should know that intuitively from driving cars and go-karts and riding in cars, not even driving. You just know that you have to slow down at sharp corners. And hopefully intuitively, that the sharper the corner, the harder it is to keep your car on the road. Anyway, the actual calculation here is centripetal acceleration equals v squared over r, 15 squared over 4. All right, you get 56 meters per second squared. What the heck does that mean? Well, that means that this car is going towards the center of this circle, accelerating towards the center of the circle at a rate of 56 meters per second squared. It doesn't end up here, though. It ends up over here. Well, if you think about it, this would go in a straight line if there was no force. So, if we counted the time it took to get over to here, well, the cart would be up here without a force. But it ends up here. So it got pulled in towards the center of the circle, going from here to here. So that's why it's directed towards the center of the circle. So centripetal force, M, this is AC. We already calculated that, v squared over r. So we can just shift that down to here, you get 11,200 newtons. There's no way this go-kart would be able to round this corner. That is way too much force of friction. If you remember, force of friction is the coefficient times the normal force. So the normal force would have to be huge, right? Coefficients of friction aren't typically much above 1. If this thing is 200 kilograms, the normal force acting on it would be about, 2,000 newtons. And keep in mind, this is if it was a flat corner. So 2,000 newtons of normal force, you'd have to have a coefficient of friction of like 5 point something. That's huge. That's not really possible. All right. Here's another one. One on the midterm. One on the final. Very similar to this. Rubber stopper goes around in the circle. The centripetal force is again acting towards the center of the circle. The centripetal force in this case is the tension in the string. It's not some magical force that appears. How big is the tension in this string? Well, Fc equals mv squared over r. So that depends on the mass of the stopper, its speed, and its radius. Well, we know the speed, we know the radius, and oh, look, we know the force of tension is 40 newtons. So what must the mass be? 0.41 kilograms. Very good. Algebra here we did in class. You guys have made great strides on your algebra this year. I'm going to do some more algebra practice last year because that's a really valuable thing to take on with you in college. Just being good and proficient at algebra. It'll help you. Even if you're not a science or math major, you're going to have to do algebra at some point. So mv squared over r, F equals mv squared over r. We multiply both sides by 2, divide both sides by 14 squared. Mass is 0.41 kilograms. This one down here, it's just a reference to the simulation lab. Decrease the mass on both, of one or both, I should say. So the force will go down if one of these gets less mass. It's always equal and opposite. So changing one affects the force on both, you know. And then we just do the calculation, G m1 m2 over r squared. So I just took the numbers off of the illustration here and plugged them into the force of gravity equation. Let's not worry about that too much. 0.000027, 0.000027 rounded. So it checks out. Anyway, I'm just gonna keep going here. Make it one big monstrous video that take forever to upload to YouTube, but then we're done. All right, static electricity. Awesome. There's a lot of definitions here, which I'm gonna rip through really quick. Charge, it's a fundamental property of an object, of matter, really, of matter. But what is it? Again, good question. It's positive and negative. Well, it's a property of electrons and protons. Just like mass is a property of electrons and protons, what is it? Well, it's its existence. Charge is also its existence. It's like just fundamental. Very hard thing to define, so to speak, but pretty easy to observe how charged objects behave. Coulomb, that's Augustin Coulomb, is named after SI, base unit of charge, capital C. Fundamental charge unit, well, that's when the charge unit of a proton we call +1, and it's E. Electron, -1. It's kind of a nice way to keep track of charge, and it's often the way we do it in chemistry and other sciences, but when we want to actually start doing calculations of force, we got to convert it to coulombs. Either that or we need a different version of the electrostatic constant. But anyway, positive, it's a convention, right, of type of charge. A proton is positive. We just call it positive. +1 or +1.6 times 10 to the -19th coulomb is a proton. Electron is negative. What does that mean? It's just totally convention. It could have been called green and red or something, or I don't know, just two random words, but it came up with positive and negative. Okay, great. Polarization, neutral, no net charge. So a neutron is neutral, has 0 charge, literally no charge. A neutral object, there's no net charge. Just meaning that means that there's the same number of protons and electrons, so there's no net charge. Polarization, that occurs when an object has positive on one side, negative on the other, You know, when the charge is separated, charge separation, one side's positive, one side's negative, right? Maybe I could do positive, negative. I don't know. Rock, paper, scissors. Conductor, that is a material in which electrons are free to move about the surface of it. So metals are typically good conductors. The Fermi electrons in a metal are allowed to move around on the surface, so you can put in a force on those electrons and then they can move. Insulator, you can put there's electrons on insulators. You can put electrons on insulators. You can take electrons off of insulators, but if you apply a force to the electrons on an insulator, they can't move across it. They can shift a little bit, but they stay stuck in their molecules. Conductors, they don't stay stuck in their molecules. They can move around. Electric field, this is the force field produced by charged objects or by protons and electrons. There's the electric field of a proton. There's the electric field of an electron. That's what they look like. Let's see, polarization, when an object has positive, oh no, sorry, what am I doing? I went backwards. Electric potential or voltage. So the reason I introduce this here is because we're gonna need it in a minute for chemistry. It's the energy available per unit charge in an electric field. Volts are joules per coulomb. The key word there is energy available. It's energy available per coulomb of charge, joules per coulomb. So battery provides energy. Electric fields provide energy. Nothing has energy until there's an object placed in the electric field. So that's a subtle thing to know, but don't worry so much about this. Circuits, we kind of got the intuition of what voltage is from circuits. Fe equals K Q1 Q2 over R squared. You know, Fe equals QE. E equals Fe over Q. Okay. That's Coulombs Law. K Q1 Q2 over R squared. K is 9 times 10 to the 9th newtons times meter squared per coulomb squared. I guess I should put that up here, electrostatic constant. That'd be a good thing to know. R is the distance between the two charged objects. K is the charge of each object in coulombs. You can also calculate electric force if you know if you only know one of the object's charge and then the electric field strength from one of the other objects. So electric field strength is units again of newtons per coulomb. That's up here as well. Usually electric fields, you just got to remember about this is they always come from a charged object. They just don't appear. They always come from an electric or charged object. So somewhere over here, maybe there's a big positive plate of charge and then there's electric field coming off of it. Then you put another little electron near it and it gets pushed away. Cool stuff. Remember opposites attract, so similars repel. Remember this one, neutral objects will attract to both positive and negative objects because of polarization, right? So you bring a big positive charge near something that was initially neutral, the neutral object will get polarized, right? The electrons in this neutral object will get drawn closer to this. Now, in a conductor, the electrons will go all the way to the surface of the object, right? Because they can move a far distance. In an insulator, the individual molecule is polarized, right? So I only made one drawing here just to kind of show the general idea of polarization. But polarization of a metal is much greater than the polarization of an insulator. So neutral objects, be it a piece of plastic, a piece of metal, they'll always attract to something charged because the charges in the object will move a little bit. And when they move, you know, now this side's more negative, this side's more positive, this side's farther away from this object here, so this side experiences less force of repulsion than this side experiences force of attraction, right? So if I drew an arrow of the force, the electric force on each side, this one's got more force, so there's a net force towards the charged object. And if these were all negative, then this side would be positive, this side would be negative, but the force arrows would end up still looking the same. Pretty cool stuff. The calculations here, how does something get charged? Well, electrons have to be added to or taken away from an object. And I'm so proud many of you said this pretty quickly when we did review, so I was happy for that. So a neutral object, if you take away 3 electrons, there go the 3 electrons, this is now positive. All right? If I added 3 electrons to a neutral object, now it would be negative. How does something get polarized? Electrons get shifted from an outside E field. So you start off with something neutral. If you put this object near something that's making an electric field, right? The electrons are going to get drawn upstream. The protons are going to get pushed downstream. The protons don't actually move, but what happens is you almost want to think about these 4 electrons getting pulled off of these 4 protons. So that's why this polarization occurs. 2 electroscopes are charged with 90 nanocoulombs. Oh, we got a prefix here. We've got a prefix, people. Oh, that equation sheet doesn't have the prefix on it. Hold on a second. Okay, here we go. Prefixes, micro, nano, right? So nano, 10 to the negative 9th. So all I'm doing is when I write down Q, I do 90, I get rid of the N, I make it 10 to the negative 9th. K, this is a constant. K is right. Oh, need the back page. Right. Chia. 9 times 10 to the 9th. Newton meter squared per coulomb squared. Bam. All right, so plug everything in to your calculator. 0.25 is the distance between them. You get a small force. You don't have to write this in scientific notation, but you can. Here's one using electric field force. We got a big negative plate. The electric field goes towards it. If I put a little positive charge near it, with 20 microcoulombs, positive 20, it would get drawn towards it, right? So the electric field strength is 4,000 newtons per coulomb. So it's 4,000 newtons of force per coulomb of charge. All right, so electric force equals QE. Q is 20 times 10 to the negative 6 coulombs times 40,000 newtons per coulomb. Multiply them, 0.8 newtons. Draw the electric field around a positive charged sphere. The electric field goes out. That's in your notes on the previous page. All right, one more electrostatics question. Video's getting kind of long, but oh well. Q1 equals 200 microcoulombs. Q2 is unknown, but we know the electric force is 1.5. In fact, we also know that the electric force in this one would have to be negative 1.5. It'd be getting pushed to the left. They have to have an equal and opposite force, right? Force on Q2 due to Q1 has to be equal to the force on Q1 due to Q2. All right, so electric force equals K Q1 Q2 over R squared. All right, we know it's 1.5 newtons. We know K, we know Q1. We're looking for Q2. The algebra here is annoying. We have to multiply both sides by 30, so 1.5 times 30. That's how I got this top part of this equation. All right. Then I still have, I got to divide both sides by 9, multiply both sides by 0.3. That's how that gets up there. 9 comes down here. This comes down here. You get a number with a lot of decimals. There you go. All right. Circuits. Energy, voltage is your energy per coulomb of charge. V. Current is the flow rate of electricity, flow rate of coulombs of charge. So current is coulombs per second or amps. Energy lost in terms, energy loss in items due to this. So what the heck does that mean? Due to this resistance. So resistance is the resistance to current flow, right? It's a hard thing to define. It dictates how much energy is lost. So it's volts per amp. It's the energy lost per amp of current in an item, or ohms. Power is the energy used per second, so the power consumption. So there's a relationship clearly between resistance and power, right? The power use is going to depend on the resistance, but also it depends on how much voltage is pushing. Current, you don't really control. Current responds to the voltage and the resistance. Anyway, Series, that's when resistors are in single file line. Parallels when they're next to each other. Equivalent resistance is the total resistance of a circuit. Now, keep in mind, it's not just necessarily just the simple sum of the resistances, right? It's the equivalent resistance. That's why we call it equivalent resistance and not just total resistance. I mean, the graphs and diagrams, it's just it's just your equation sheet, you know, there's not even really anything to add. I give you so much on this equation sheet, right? You know, so when I look at the equation sheet, what I'm saying is, okay, in a parallel circuit, since all the resistors are connected directly to the battery, this is just a wire, right? So they're all connected to the positive side of the battery. They're all connected to the negative side of the battery. They all must have the same voltage. All must have the same voltage. But the current, what happens is the current flows out of the battery, hits this junction, it splits. All right? Splits to some value here, some value here. Let's say it was 1 and 3. All right? 1 and 3. Well, that means 3 is flowing into this junction, would split into, let's say, 2 and 1. So 1 comes in here, 2 goes here, it gets down to here, it recombines, it's 3. Let's say this is 1 and 3, recombines, it's 4. So the current supplied by the battery gets split up between the resistors. So current through this one, plus the current through this one, plus the current through this one have to equal the current being output by the battery. For a series circuit, right, if you go through the battery, the current never branches, right? So that means everywhere in this circuit, the current has to be the same. So the current supplied has to equal the current through 1, equal current through equal current through 3. Ends back up here. All right? The current supplied has to equal the current through each individual resistor. All right. Equivalent resistance, you just add them for series, but when you add them in parallel, the resistance actually goes down, so it's kind of a weird formula. We'll look at that in a minute. Let's go to the problems. Simple circuit set up with a light bulb, wires, and a 6-volt battery. Simple circuit, there's only one way to set it up, right? Battery, bulb, or battery resistor. There you go. If the bulb draws, oh, it's a light bulb, not a resistor. 0.2 amps of current, so 0.2 amps. What must the resistance of the bulb be? So this bulb is going to have to have a voltage of 6 volts. Is it in parallel with this or series with it? Well, it's actually both, right? So there's no branch offs. It's in series, I would say. But it's also like it's in parallel because they have to have the same voltage because there's nowhere else for the voltage to be lost. So anyways, voltage equals current times resistance, divide both sides by current, R equals E over I, 6 volts, 0.2 amps, 30 ohms. Power used, current times voltage. Now, there's other ways to calculate the power subbing in Coulombs Law. We didn't really do that. We usually just use this formula. Current times voltage, 0.2 times 6 volts is 1.2 watts. Very good. Simple series, simple circuit. Awesome, easy, fun. That is 95% of what you should know for circuits for your daily life, you know. But anyway. And yes, your daily life. Circuits are super important. So battery, right? Resistor. 2 resistor circuit. Very nice. So the circuit shown, these questions are a little bit different than how we had done things in class. They're just a little more, I don't know, a little more interesting, let's say. Circuit shown above draws 0.2 amps of current out of battery of unknown voltage. Okay, determine the voltage of the battery. Well, if you know the current supplied is 0.2 amps, and you know this resistor and this resistor, so I1 also has to be 0.2 amps, I2 also has to be 0.2 amps, you can do V equals IR for each resistor, right? This one must be 5 volts. I times R for R1 is 5 volts. V2 must be 9 volts. I times R, right? So 5 volts and 9 volts are the voltage drop across each resistor. And because it's a series circuit, you know that the battery supplied has to be split up, has to add, the individual resistors have to add to equal the battery. So you just can add them together. and you get 14 volts total. So the battery must be 14 volts. And then it says determine the power used by the 45 ohm resistor. We just pull the voltage and current of that resistor, 0.2 times 9 volts. That resistor's voltage is 9 volts, and we get 1.8 watts. So that's it's kind of like the way we calculated the current in the parallel circuit that we looked at for the quizzes, right? We found each individual current and then add them together to get the current supplied. Well, in this case, we find the individual voltages, add them together to get the voltage of the battery. The parallel circuit here, kind of a similar interesting question. The circuit above is set up and a combination of resistors draws half an amp. All right. Determine the current flow through the unknown resistor. Oh, wait a minute. What the heck? Well, again, we know that each one of these has to have 6 volts, right? 6 volts, 6 volts. So this resistor here, we can figure out what I1 is, right? If we know I1 and we know 0.5 amp is supplied, remember that 0.5 amp comes into this junction and it splits. Splits here, goes down here and over here. So 0.5 amps, whatever this current's going to be, whatever's left over must be flowing through this resistor. So let's see what we got here. I supplied has to equal I1 plus I2. So 0.5 amps is current supplied. Let's figure out what this one's current flow is, I1. So it's I1 is I is V over R. So 6 volts divided by 20 ohms gives us 0.3 amps. Oh, well, that's good. So we've got 0.5 flowing into that junction. We've got 0.3 amps flowing down. What does this one have to be? Well, 0.2 amps it must be, right? The current through this resistor has got to be 0.2. Whatever flows into the junction must flow out. Determine the value of the unknown resistor. R1 equals V1 over I1. 6 volts over 0.2 amps. 30 ohms. 30 ohms. All right. Just, we know the voltage of the current. There we go. All right, that brings us to the end of a long video. But, you know, if you have any questions over the next couple of days, email me. Physics equation sheet, maybe I should post a PDF of that in there as well. I'll do that. All right, have a good one.